All right, hello everyone, welcome back. We're going to go ahead and finish up the second part of Standard 3 in calculus. In part 1, we looked at how to use a table or a graph to evaluate a limit and what a limit is, when it exists, when it fails to exist. The final part of how to evaluate a limit is to do so analytically using some basic limits and some basic properties of limits. So I know there's a lot on this page here, but let's focus on these basic limits so far. The limit as x approaches some constant c of b is equal to b. B is some other constant. So b is independent of x. No matter what x is, this constant b is not going to change. All right, so for example, say I have the function f of x equals 3. No matter what x is equal to, because 3 is independent of x, the value of the function is always going to be equal to 3. So applying that same principle here, the limit of some constant b as x approaches c is always going to be equal to b. Part 2, the limit of x as x approaches c is equal to c. So this is basically just direct substitution. When I substitute x into our function f of x equal to x, I'm going to get the same value back out. So as x approaches any number, the value of x would be that same number. So as x approaches c, the limit of x would simply be equal to c. Part 3 is another example of direct substitution. The limit as x approaches c of x to the nth says, all right, substitute c in for x and we'll get c to the nth. Here in this next table to the right, we have some properties of evaluating limits of two functions, either f of x or g of x. The limit of f of x as x approaches c is defined to be equal to L, and the limit of g of x as x approaches c is defined to be k. So we have several different limits right here. First is called scalar multiple. The limit of x approaches c of some constant b times f of x means you can just take that constant b times what the limit of f of x as x approaches c is equal to, in this case L, so b times L. The sum or difference in part 2. The limit as x approaches c of f of x, either plus or minus g of x, will be equal to what those limits are equal to, either L plus or minus k. Product and quotient, very similar. When I'm multiplying f of x times g of x, take the two limits and multiply them together. So L times k. The limit as x approaches c of f of x times g of x is equal to L times k. If you're dividing f of x by g of x, then take L divided by k. You have some function to a power. The limit as x approaches c of f of x raised to the nth would be L to the nth. A composite function, functions and sides of functions. Says to take the limit as x approaches c of f of g of x by taking f of k. Since the limit of g of x as x approaches c is equal to k, I'm going to take that k value and substitute it into f. Now, there are other rules for polynomial functions, radical functions, and trig functions. But the overarching principle of everything on this slide says if you can plug your constant into the function for your limit and get a value out, if it's defined, use direct substitution. That's going to work more often than not. We'll look at a couple of cases where it doesn't work and how we can maybe use a little bit algebraic simplification technique. But if you can plug it in, plug it in. All right, so let's look at a few of these limits and examples here on this slide. First up, what's the limit as x approaches 2 of 3? Notice that it's just 3. No matter what x is approaching, in this case it's 2, it could be anything. It's going to be equal to 3. On part 2, what's the limit as x approaches negative 4 of x? Well, substitute negative 4 in for x, and we're going to get negative 4. On part 3, what's the limit as x approaches 2 of x squared? We'll substitute in 2 for x. So 2 squared would be equal to positive 4. We can do the same thing over here on this snapshot of some problems. Substitute all these values in. The limit of 4x squared plus 3 as x approaches 2. 4 times 2 squared plus 3. That's 4 times 4, 16 plus 3, or 19. Plug in 1. 1 squared plus 1 plus 2 is 4. Divided by 1 plus 1 is 2. 4 divided by 2 is 2. The limit as x approaches 3 of the cube root of 2x squared minus 10. So 2 times 3 squared minus 10, that's going to be 2 times 9, which is 18 minus 10 is 8. Take the cube root of 8, and we'll get 2 again. The limit as x approaches 0 of the tangent of x. Substitute in 0 for x. Evaluate that as by doing the tangent of 0. The tangent of 0 should be 0. Take the limit as x approaches pi of x times cosine x. So this would be pi times the cosine of pi. The cosine of pi is negative 1. Pi times negative 1 is negative pi. Now you can always check these using a table or looking at a graph, but since I can do this by direct substitution and evaluate the limit, we'll use this method. Okay, so that's pretty easy. What about when direct substitution fails? These last couple slides are some algebraic strategies to look at what happens when direct substitution fails. The theme here is that we need to make a new function that agrees with our given function at all but one point. So look at these two pictures. I have the function f of x equals x cubed minus 1 divided by x minus 1. Looks like a pretty basic parabola, except that x equals 1, the function's undefined. I've got a second function, g of x, which is equal to x squared plus x plus 1, which is exactly the same, except at x equals 1, I've taken in that open circle, I've defined it to be equal to 3. It agrees with my original given function at all but one point for when x equals 1. The limit cannot be found by using direct substitution originally, but I can here, because I can plug in 1 and get out a value 3. The function is undefined as it's given. If I make a new function where I can plug in 1, I can use that new function that is almost identical to it to find the limit. So let's practice that. Find the limit as x approaches 2 of x cubed minus 8 divided by x minus 2. So what we're going to do is use little synthetic division to make a new function where I can plug in 2. Because I can't right now. I would get 8 minus 8 divided by 2 minus 2 is 0 divided by 0, which is undefined. So let's go ahead and simplify this using direct substitution. We'll do 2, and then I have 1x cubed, 0x squared, 0x, and negative 8. So using our table, we'll bring down 1. 2 times 1 is 2. 0 plus 2 is 2. 2 times 2 is 4. 0 plus 4 is 4. 2 times 4 is 8. Negative 8 and 8 makes 0. So I get x squared plus 2x plus 4. And now I can take the limit as x approaches 2. This would be 2 squared, which is 4, plus 2 times 2, which is another 4, plus 4 more. So 4 plus 4 plus 4, or 12. Okay. Let's look at maybe one more of these examples. How about the limit as x approaches negative 3 of x squared plus x minus 6 divided by x plus 3? I'm going to try and take the limit as x approaches negative 3. So if I do that, I would be dividing by 0. So direct substitution fails. Let's see if we can simplify this original function. We have the limit as x approaches negative 3 of x squared plus x minus 6 divided by x plus 3. Let's see if we can factor that. X squared plus x minus 6, that's going to factor into x plus 3 and x minus 2. Bring across the dividing by x plus 3, and notice that I have the same factor on top and bottom. So this original given function, x squared plus x minus 6 divided by x plus 3, simplifies to simply just x minus 2. So I can evaluate this limit as x approaches negative 3 by using direct substitution for when x in our function x minus 2. So negative 3 minus 2 is simply negative 5. Of course, this can be confirmed by making a table or looking at a graph. We went ahead and used factoring to simplify this function to get to a new function that agrees with the original given one at all but one point. Here I couldn't plug in negative 3. The function's undefined. Here I can. So now I can use direct substitution and evaluate my limit. Another process of trying to evaluate limits using some properties from calculus and algebra is something that's called the squeeze theorem. The squeeze theorem kind of acts like a sandwich. I'm going to sandwich some functions together. So looking at our picture, I have 3 functions, h of x, g of x, and f of x, that are always defined by this inequality. If f of x is less than or equal to g of x, which is less than or equal to h of x, for all x in some interval containing c, or I guess it's actually going to be a down in this picture, but you get the same idea. It's just some constant. And the limit of f of x as x approaches c is equal to L. And the limit of h of x as x approaches c is also equal to L. Then since g of x is always between f of x and h of x, since it's always greater than f and less than h, wouldn't the limit as x approaches c of g of x also have to exist, and it would also be equal to L? I kind of smush all of these functions together. And when they all come together at that one point, I know they all have to have the same limit for that value. If I know the limit of 1 on top and the limit of 1 on bottom are both equal to some number, in this case L, the one in the middle also has to be equal to L. So this is going to be helpful in defining some special trig limits. These right here are some really important special trig limits. The limit as x approaches 0 of sine x divided by x. Note that we can't plug in 0 right away. Direct substitution fails. And there's no real great way to simplify sine x divided by x. But we can use what's called the squeeze theorem to end up evaluating this limit. So let's do f of x equals sine x divided by x. Notice that my function's undefined, like I said, at 0. But if we can make some functions that are strictly greater than and strictly less than sine x divided by x on some interval, if we know the limit of those two functions, we can assume that the limit of sine x divided by x would be equal to the same thing. So let's do, you could do lots of different things. Might do, it'd be x squared plus 1. And maybe h of x equals 1 minus x squared. Notice that sine x divided by x is always going to be the one in the middle. I'm squeezing, smushing, sandwiching that undefined function as x approaches 0 between two that I know. I can plug in 0 to x squared plus 1, our top function, and 1 minus x squared, our bottom function. When I plug in 0, I get 1 on top, I get 1 on bottom. When I plug in 0 to the top function, I get 1. When I plug in 0 to the bottom function, I also get 1. So it would stand to reason by any kind of just basic logic that wouldn't the 1 in the middle also have to be equal to 1? That's what we've done here. The limit as x approaches 0 of sine x divided by x is equal to 1. Also do the same thing for another trig function. 1 minus cosine x divided by x. Cannot plug in 0. It is undefined. Cannot simplify. So let's see if we can't come up with some different functions. Maybe we'll use a different one, like maybe the absolute value of x. And negative absolute value of x. Note that the one that we want to smush is in the middle, and they all kind of come together at 0. One is strictly greater than 1 minus cosine x over x. One is strictly less than 1 minus cosine x over x. I can plug in 0 to this function and get 0. I can plug into this 0 to this function and get 0. So according to the squeeze theorem, wouldn't the one in the middle have to have a limit that's defined to be equal to 0 as well? And that's the case. The limit as x approaches 0 of 1 minus cosine x divided by x would be equal to 0. So let's see if we can't use that to simplify some of these kind of difficult looking trig function limits. So first up, we have the limit as theta approaches 0 of the cosine of theta times the tangent of theta divided by theta. Okay, let's see if we can use a little bit of trig identities here. I know that the tangent of theta is equal to sine theta divided by cosine theta. And now we can start simplifying. That cancels with that. I'm left with the limit as theta goes to 0 of the sine of theta divided by theta, which, as we know from our work with squeeze theorem a second ago, has to be equal to 1. Let's try another one here. How about the sine of 4x divided by x? What is the limit as x approaches 0 of the sine of 4x divided by x? Now, how is this different than the one we're given here? I have the sine of x divided by x. That limit as x approaches 0 is equal to 1. Well, here, this is the limit as x approaches 0 of the sine of 4x divided by x. There's an extra 4 right there. So one trick we can do is make use of a clever form of 1. We're going to multiply the top and bottom by 4. So let's think of this as the limit as x approaches 0 of 4 times the sine of 4x divided by 4x. Now see how these two terms agree. The sine of 4x divided by 4x. They agree just like these two terms did over here, the sine of x divided by x. So it would stand to reason that this would also be equal to 1. The limit as x approaches 0 of sine of 4x divided by 4x would be equal to 1. So we have the 4 up above times that limit, which we know to be 1, which is 4. If this was the sine of 5x divided by x, the answer would be 5. If this was the sine of 10x divided by 10, the answer would be 10. Using the squeeze theorem. All right, one last thing when it comes to limits is something a little bit new. We've been looking at what's called two-sided limits. All these different limits have been two-sided. Well, what if we only look at a limit from strictly one side, from either the left or the right only? Certainly can. It would just be what's called a one-sided limit. Up until now, in order for a limit to exist, it has to be equal to the same thing as I approach some value from the left and from the right. Well, that's no longer the case. If I'm looking at it from one side, it doesn't matter what the other side's equal to. There's a little bit of notation that is worth noting. It says here the limit from the left is defined to be the limit of f of x as x approaches c negative. C with the little negative symbol up on top. Let me kind of write this out. So from the left, the limit as x approaches c negative of f of x. And from the right, from values that are greater than c, the notation is x approaches c positive of f of x. It's a one-sided limit when I have either a positive or a negative. And that also indicates the direction. When it's negative, it's from the left. When it's positive, it's from the right. Over here, we had two-sided limits because we had no little positive or negative symbol. Okay, so let's use that to investigate some of these limits. In our picture, what is the limit as x approaches 0 from the left? As x approaches 0 from the left, from values that are less than 0, my function's getting closer to 0. Now, what about the limit as x approaches 0 from the left? I'm sorry, as x approaches 0 from the right. So now that we're going to do 0 positive right now, 0 positive. As x approaches 0 from the right, my function's getting closer and closer to 1. I don't care that the two-sided limit fails to exist. I'm not trying to figure out what a two-sided limit is. In this case, these are just strictly one-sided limits. The two-sided limit fails to exist because each of these one-sided limits are different numbers. I approach 0 from the left-handed side. I approach 1 from the right-handed side for this piecewise function in the graph below. A little bit different notation, but it follows the same process as you would normally think for a limit. It has to approach some number, but now we're just approaching it from one direction as opposed to two. So that should wrap up standard 3. We'll see you again next time.